In this lesson, we're going to look at Objective 5.1 reaction rates. So the learning objective states that we should be able to explain the relationship between the rate of a chemical reaction and its experimental parameters. So this entire unit is going to be focused around how fast or slow a chemical reaction occurs. And we can actually measure these chemical reactions, which we will say instead of fast or slow, we'll end up actually just calling it the rate at which it occurs. Generally, a rate will be expressed in the quantity molarity. So we talked about molarity, which is just concentration per unit of time. What ends up being what rate is. So the kinetics of a chemical reaction is defined as the rate in which an amount of reactant is converted to products per unit of time. So here it's going to look like this. Brackets, remember, are going to indicate molarity. So this amount that is mentioned is talking about the molarity concentration. And then T, this per unit of time, time can be seconds, hours, minutes, doesn't matter. You'll just be notified what it will be. One of the biggest things though is when it comes to a rate, it's always about the focus of the reactants, because the reactants are going to be our starting materials. You don't have products until your reactants have started. So we generally will be looking at reactants when it comes to figuring out rates, but we can also see what the rate would look like for products being made too. So just a little quick refresher on molarity and concentration. So as mentioned, the brackets mean big M molarity, or molarity is moles over liter. So a few things that we may need to know or be reminded: 1,000 milliliters are in a liter. Also, you can convert between grams and moles and grams with molar mass. So don't forget that. Might be useful to just be refreshed on that. But yeah, molarity is N over V, moles over volume, which is volume being in liters. So let's consider the reaction that we did in our lab, percent of copper and brass. So here is that reaction again. We had brass, which ended up being the copper in this reaction. Remember, brass is made of copper and zinc. We react it with the nitric acid, the super concentrated nitric acid, and that produced three things. We made that toxic brown gas, nitrogen monoxide. We then made our copper 2 nitrate solution. It was blue, and we also did make water as well. Now, when it comes to that reaction, there's actually numerous ways for us to measure the changes for that reaction. All right. Now, obviously, the only way that we actually utilized measurements in that lab was looking at the concentration of the copper 2 nitrate produced. So I'm going to put that as the first one. So here, data we can collect is figuring out the concentration of copper 2 nitrate by a colorimeter. We could also, if we had more fancy equipment, we could have used a spectrophotometer. That could also have been used as well. Still will get us the same answer. And this was because it was a blue solution that we made. Okay, so that was one way for us to look at changes for this reaction. Another way that we could have changed the reaction to not be about measuring the copper 2 nitrate or measuring the copper and brass, we could have looked at things involving like pressure and volume. So we could have looked at the volume of the nitrogen monoxide gas produced. Now, obviously, when we had that reaction occur, we just had the nitrogen monoxide get ventilated, and we weren't even going to have anything to do with it. So if we wanted to see how much volume was produced, we could have done water displacement. My only thing about water displacement, it may not have worked the best just because nitrogen monoxide is a polar compound. And so when we talked about like dissolves like, NO and H2O, both would have similar intermolecular forces. So it may not have been the best option. Another thing is we could have looked at pressure changes. So if the experiment was done in a sealed container. We could have actually looked at pressure changes. And so here, because we would have made that nitrogen monoxide gas, that would have changed the pressure inside that sealed container, but obviously we didn't have a sealed container. And then lastly, we could have looked at mass lost by reaction, because gas produced would escape. Now, you're probably wondering, well, how would we know how much left? Well, if we think about the law of conservation of mass, we would have known how much the mass of these two together were. So if we let the reaction proceed till the reaction stopped, we could weigh the mixture together before and after, and that difference would tell us how many grams of nitrogen monoxide we made. So those were just different ways for us to use any quantitative analysis that we could have gotten from this experiment. Now, obviously, the one we did in our unit 3 and 4, we ended up looking at the concentration of the copper 2 nitrate. We ended up figuring out the mass percent of copper in brass. All right, moving on. So general equation, just coming back about reaction rates. So if we look at this general expression, the capital A, B, C, and D all represent chemical species. So my capital A and B are reactants, my capital C and D are products. So then the lowercase a, B, C, and D are just going to be our stoichiometric coefficients. So we can actually define the rate of the reaction by two ways. The first way is taking the final minus initial amount. And here, that amount is referenced towards concentration, as we had mentioned previously. I do want to note, when we do final minus initial, that's what that delta means. Delta means the final minus initial. That is why you'll see it right here. All right, so if you do final minus initial by the concentration, and then final minus initial by the time at which it occurred, that time frame, you can figure out the rate of the reaction. So if you come back to this side, you will notice I have written the rate in that same format that I have to the left, this part right here. And so I took every single species, and you will notice by their coefficients, I ended up, I'm going to highlight this here, the coefficient ended up going in the denominator, okay? But I took the concentration of that species, so the change in concentration, divided by that amount of time, and you end up dividing by its coefficient. And we'll get together here shortly and show why we would divide, because when we do mole ratios, it makes sense for us to put it on the bottom. Now you will notice that some of these actually have negatives and the others have positives. So this part right here are A and B. These are our reactants, so they're being consumed in the reaction. So we actually call this the rate of disappearance. Because what's happening is you're going to be seeing that our concentration is going to be decreasing. Okay, so here we would get a negative number, and so that would help us figure out how much it's changing by the amount of time. And then you will notice our products have positives. Okay, we call this the rate of formation. You also might see rate of production as well, anything to reference that we're talking about producing something, okay? But here they'll have positive because when we do final minus initial, they will get positive values, okay? All right, so moving on. So going back to the reaction that we were talking about on the previous page, the percent of copper in brass lab. This is just some, I wouldn't say fake data, but we're going to analyze this data. So this data was collected by 50-second intervals. Okay, so I have time 0, 50, 100, and 150. You will notice the second and third column HNO3 is one of my reactants, concentration. And so here, this is showing its initial concentration, 8, and you'll notice that it's decreasing by 2 after every 50 seconds. So in the first row, you're just going to notice that this is time 0. Nothing has happened yet. So my initial is still here, and we hadn't made any of the copper 2 nitrate, and so we don't have a rate just yet, okay? Now for these two columns right here, we're going to look at the mole ratio. I want you to think stoichiometry, and we're going to be seeing how much nitric acid has been consumed to make our product, our copper 2 nitrate. So the mole ratio between nitric acid and copper 2 nitrate, looking at my balanced equation, is 8:3. So for every 8 moles of nitric acid, that is 3 moles of copper 2 nitrate. And again, this is from the balanced equation. All right, so I'm going to zoom in here. So after the first interval to get us to 50 seconds, our nitric acid consumed by 4. So here, if I take, I'm going to highlight these all yellow because it's going to come into play soon. So here, we're going to do a mole ratio between nitric acid and copper 2 nitrate. So here, 8 moles of nitric acid for our 3 moles of copper 2 nitrate. Here, when we do 4 times 3 divided by 8, we will make 1.50 molar of our copper 2 nitrate after those 4 moles were consumed, okay? Now, I'm going to continue this down because we're going to do this for every single one. Now, they're all going to have the same ratio. I'm just not going to write the chemical species for the other one. So here, in the next time interval, 2 times 3 divided by 8 gets us 0.75. Now, please note, we already have 1.50 right here. So I'm going to take this value and add them together. Now my concentration is 2.25. And that makes sense because it wouldn't make sense that we now have our concentration at 0.75. That doesn't make sense. So adding to the already 1.5 can get us the for sure new concentration. And also, let's be honest, these values after each time interval are going down. And then for these, because they're products, this is a product, we will be increasing for this. Then here, 1 times 3 divided by 8, I get 0.375. Let's add that to the 2.25. I now have 2.63. All right. So now we're going to move on to the next 2 columns that talk about rate of our chemical species. You will notice I have one for the rate of the reaction, which I'll talk about last, but now we're going to focus on, let's figure out what the rate of nitric acid was and the rate of copper 2 nitrate. So, as mentioned previously, we talked about figuring out rate, okay? We always do final minus initial. For the amount being the concentration, divided by final minus initial for time. So I'm going to zoom in for the nitric acid. So here we want the change in concentration and the change in time. So we're going to be looking at the interval with the 0 time and then the 50, because we are going from 0 to 50. And then the next one we'll do 50 to 100, and then the next row 100 to 150. So here, the change in concentration went from 4 to 8. And that time interval was 50 minus 0 seconds. And so here, we are going to get negative 0.0800 molarity per second, all right? And again, this makes sense that the rate is negative because this is the rate of disappearance. I'm going to do this for the rest of the nitric acids, and then we can do the copper 2 nitrates together, okay? I'm not going to show, I didn't mean to erase that. I'm not going to show this expression here, but I will show the work for it. So then for the next time interval, we will do 2 minus 4, and that time interval was 100 minus 50 seconds. So here that is minus 0.0400 molarity per second. And then lastly, we will do 1 minus 2 divided by 150 minus 100 seconds. Here you get negative 0.0200 molarity per second. So again, what this value that we just got tells us, how much concentration is being consumed or disappearing, that's how much concentration per 1 second, okay? All right, going to the copper 2 nitrate, we're going to do the same thing here, the change in concentration per that change in time. Here, this will be 150 minus 0, and then 50 minus 0 seconds. Here I get positive 0.0300 molarity per second. And I'm going to continue the rest of the other boxes. This one I get positive 0.015. And if you're like, well, you know what, I'm kind of noticing a trend, you're definitely right, okay? There is definitely a trend with all of this, and we will start clicking things together over the next couple of objectives. All right, lastly, this is 0.0076 molarity per second. All right. So we have found our rates at each of those time intervals. It's okay, but just realize that over time, the reaction was slowing down. It didn't stay constant. You can see that at first we were really getting a lot of nitric acid consumed, but then it started to slow down. That's totally okay. You just have to realize that reactions slow down over time. All right, let's talk about the rate of reaction. It's going to have the same units as the rate of our chemical species. But for this, I want us to think about talking about the entire reaction. All right. So I'm going to zoom in this bottom corner. If you want to find the rate of the reaction, you need to take the rate of species, and I'm going to tell you it doesn't matter which one you take, and you divide by the coefficient of that species. When I say species, I'm talking about that reactant or I'm talking about that product. So if we look up here, if I use nitric acid while ignoring the negative, so I'm going to take the rate 0.0800 molarity per second, and its coefficient in the balanced equation is 8. I get 0.100 molarity per second. Now, if you're like, well, why didn't you do the copper 2 nitrate? Well, if I did that in my tiny box next to it, if I did using copper 2 nitrate, and you don't have to do this, I take 0.0300 molarity per second, and its coefficient is 3, I still get the same answer. Okay, so it doesn't matter which chemical species it is. You're gonna, if you wanted to get the actual rate of the entire reaction, it doesn't matter which one you choose. All right, so I'm gonna use nitric acid for the rest of the time intervals. So let's see what they are. So nitric acid was 0.0400 molarity per second divided by 8. I get 0.00500 molarity per second for the rate. And then for the next time interval, I get 0.0200 molarity per second divided by that same coefficient. I get 0.0025 molarity per second. All right. So I know we just did a lot of data and putting it all together. I do just want to point out you can, in all these last 3 columns, all this is telling us, this tells us in whole how much concentration is changing per second. then these two columns actually starts analyzing one of the chemical species and seeing how much they're either being consumed or they're being produced. This is, in a sense, taking more of an average, okay? All right, let's consider another reaction, okay? So here I have a reaction between hydrogen and iodine, all right? Here I have making hydrogen iodide. So you can see in this table right here. One thing I want to note, and this is going to come into play here in the next couple of units, here the HI is going up over time, which makes sense because it's the one being produced, especially because concentration's right here and time is right here. And then our H2 and essentially I2 would be this curve right here. And it makes sense because they are disappearing, they're being consumed. So if I wanted to write the rate in respect to our two reactants in one product, I'm going to follow that expression from earlier. So here, hydrogen is disappearing, so negative. It'll be the change in hydrogen. Coefficient's 1, so I'm going to leave, you don't have to put a 1 there, but it's assumed a 1's there when you do the change in time. Then I'm going to show the rate of disappearance for I2. And then for HI, this is a rate of formation. I'll put a positive change in concentration of HI divided by 2, because there's a coefficient 2, delta T. All right. Now, the reaction rate is going to be defined as the negative change in the concentration of a reactant divided by that change in time. That's why we just wrote that expression right there, okay? And again, they get negatives because they're decreasing over time, and the products are gaining over time, so positive. Now, the concentration of HI will actually be increasing at twice the rate that the concentration of H2 and I2 decreases. And I don't know if you noticed in that previous little chart we were filling in, you could really see that things were changing at different rates because of their coefficients. And so in order for the overall rate to have the same value when defined with respect to any of the reactants or products, we must multiply the change in HI concentration by a factor of 1/2. That's why we need to have that 2 right there. Now, I'm going to show you why it doesn't matter. And again, I proved it up here that it didn't matter. I proved it in this spot right here. It didn't matter what chemical species you used to figure out the rate if you just use the correct coefficient. So what we're going to do is I'm going to prove it again using the data to the right. So if you want to define the reaction rate, all right, I'm going to look at first the rate of disappearance for hydrogen. So here, minus delta H2 divided by delta T. So I'm going to look at that chart and see what kind of data I can plug in. So let me zoom in. So you can see here, let me get my highlighter. For the hydrogen, I actually have its change in concentration, minus 0.28, and I also have the time interval, 40 seconds. We're going to plug those two values into that expression. So here I have minus 0.28 molarity divided by 40 seconds. So the rate of the reaction is 0.007 molarity per second. So, hoping everything goes right, we should still get the same one if we used HI's data. Now you will notice I didn't use iodine because iodine would have been, since it has a coefficient of 1 as well, it would have the same value as that H2. All right, so here, rate of reaction is positive delta HI divided by 2 delta T. Let me just write that a little bit smaller, sorry. Okay, so let's use the data from the graph. So here you can see the change in concentration of HI and that time interval. So I'm going to plug that in right here. So positive 0.5 0.56 molarity, time interval 40 seconds. I get the rate of reaction. You're probably not surprised, 0.007 molarity per second. So they both match up. I get the rate of the reaction. Okay. All right, moving on. So I'm going to do this first one with you, and then I actually have an example for you to do as well. So let's consider this balanced chemical equation. Yes, this is a net ionic equation, just got rid of spectators, okay? So in the first 10 seconds of a reaction, the concentration of I-1 drops from 1 molar to 0.868 molar. We need to calculate the average rate of this reaction in this time interval. So we know that we can solve for a rate of a reaction, and let's write the rate of disappearance for I minus. So look at the coefficient, it is 3. So here, minus the change in concentration of I minus divided by 3 delta T. So here, let's plug in what we got from that first piece of information. So the change in concentration, it said it went from 1 molar initial to 0.868 final. So 0.0868 molar. Oh, my bad, 0.868. I was like, I didn't think it would change that much. Okay, 0.868 molar minus 1. That's an M. And then the time interval, it says in the first 10 seconds. You can assume initial was 0. So here, I get my rate of the reaction as 0.0044 molarity per second. All right, next step, determine the rate of change in the concentration of H positive during this time interval. If you want to put a 2 there, that must have been a little bit of a typo. So in this one, we have the rate of the reaction, okay? But we are trying to find out what the rate for hydrogen positive was, okay? I want you to think for this next part, stoichiometry, okay? In the sense, mole ratio. So here we can see for every 2 moles of hydrogen, that's 1 mole of the reaction. That can be used as a conversion factor, okay? So here, I know this is the rate of the reaction. I don't know why it's so spaced out like that, 0.0044 molarity per second. So if this is 1 mole of the reaction, I'm trying to solve for 2 moles of hydrogen. So here, this ends up being 0.0088 molarity per second. Now, please note, this is hydrogen positive, okay? Hydrogen positive is a reactant, so this won't be a positive 0.0088. This will be a negative because it will be a rate of disappearance, okay? Rate of H positive, and this is because it's a reactant, it's disappearing. So we're going to be losing that amount of concentration per that time, okay? All right, I have the next problem for you. Why don't you pause the video and try this out yourself? It's going to be very similar to the previous one. The only thing is I didn't give you concentration, all right? But I'm sure you guys can figure it out. So in this reaction, you end up actually figuring out that you can get molarity with moles and liters. So I got molarity as 0.0024, and they told you during each second of the reaction. So I just made it 1 second. So here it is being consumed, so I put a negative there to indicate the rate for pH3. Then it asks, what are the rates of production for P4 and H2? And so here you can use mole ratios, stoichiometry, between pH3 and in relationship to the products separately, okay, just using a mole ratio. So you can see in the bottom part, I took the rate I got for pH3, and I know for every 4 moles of pH3, it's 1 mole of P4. So I end up getting 6 times 10 to the negative 4 molarity per second for the rate. And it's positive because this is a rate of production. And then for hydrogen, I did the same thing, but the ratio will be 4 to 6. And I got positive 0.0036 molarity per second. All right, moving on. There are a few things that I want to mention, and I feel like it's better to just talk about right away, and then we'll start to dissect it a little bit more later. So there's this thing called collision theory. It is our objective 5.5, but I want you to know it's a foundation for this entire unit. So in order for a reaction to take place, there must be 3 things that must happen, and this must happen with our reactants. So the first one, particles must collide. So whenever we have reactions mean that those particles are colliding with one another. Okay, it may seem like something that is completely overlooked, and it is. So just noting that it isn't just like, oh, I mix the 2 things, it should happen. No, those particles have to collide, and then that's how bonds get broken and then bonds get formed. Next, the particles must be in the right orientation. So here, if a particle is coming this way and this one is coming this way, they are not going to collide. They have to collide, I guess, head to head. But here, the orientation actually really does matter. And we'll talk more about orientation, like I said, in 5.5. And then lastly, particles must have greater energy than activation energy. So we vaguely talked about activation energy in our last unit, talking about the energy needed or required to make a reaction happen. So it makes sense that if your activation energy is, let's say, 1,000 joules, you need to make sure your particles have more energy than 1,000 joules for it to occur, because at 990, it's not occurring. It needs to have at least 1,000. So that's why it needs to have greater energy than activation energy. Before we move on to the next part, I just want to put overall that the rates of change of reactants and product concentrations are determined by the stoichiometry in the balanced chemical equation. That's where those stoichiometric coefficients come into play, and we can look at mole ratios. And the next part of this large objective 5.1, which will finish the rest of that part right below, the rate of the reaction is influenced by a few things: reaction concentration, temperature, surface area, catalysts, and other environmental factors. So let's dive deep and let's talk about what that means. So reactant concentration. Remember, concentration is N mole over volume. So how many moles are in that volume? So the higher the concentration, the higher the chances for collisions between reactants. This hopefully makes sense. If you have a higher concentration, you have more moles in your sample. So there's more chances for those particles to collide. Versus if you had a very low concentration, the chances for collisions may not be as great. Temperature. If we increase the temperature, this means an increase of it likely to collide with enough energy that is greater than activation energy. So if you think about, if we increase the temperature, we increase the kinetic energy. A lot of kinetic energy will help us get energy that's greater than that activation energy. Yes, you could say that you increase the speed of the particles, but here temperature, when it comes to a rate of reaction, we try to focus more on the energy part. Surface area. An increase of surface area gives us a greater chance of particles colliding. So here, this would be like a fine powder is a better choice than chunks of that same material. So a finer powder actually increases surface area rather than chunks of that same species. Because if you think about it, if you had a big chunk, only the outside of the chunk is actually being reacted. Whatever in the core or inside isn't being reacted until you start getting that outside and working your way in. And then lastly, catalyst. Catalyst will actually be one of our last things that we talk about in this unit, but it isn't bad to talk about right now. So here, catalysts speed up reactions. So first thing, it provides an alternate route that requires less activation energy. Please note, you are not changing potential energy. You would just give it, oh, instead of 1,000 joules, you actually only need 500 joules, while keeping those reactants and products the same on that energy diagram. Or there's catalysts that actually alter the orientation of molecules to collide in correct orientation. So there are catalysts that end up literally taking that reactant and finding another reactant, and they're putting them in the correct orientations to react. Again, we'll talk more about these catalysts, but this is what catalysts do. It helps provide an alternate experience for those particles. All right, I have this part for you to do right now. So this example, a student is observing zinc metal and its reaction with hydrochloric acid to produce hydrogen gas and zinc chloride solution. So the student's actually measuring different ways the reaction rate between zinc and hydrochloric acid is affected by altering various conditions. So you can see I have the first column zinc, HCl, and temperature. So what you're going to do is in part A, you're going to circle in each column which one would actually give us the slowest reaction rate. And then I want you to explain your choice for why you chose that option rather than the other one. So why don't you pause the video, try this out yourself, then click play and I'll go over the answers. Right, so in each of the columns, you should have chose large chunks, 1 molar, and the ice water bath. So let's go over the justifications for those. So large chunks are going to have less surface area. So that's going to decrease the rate. Then the 1 molar, there's going to be less moles present, so less chances for collisions. And then lastly, if we're in an ice water bath, colder temperatures, yes, our particles are going to be moving slower, but the biggest thing is you're going to have less energy, and it also will be less likely to collide with enough energy that's greater than the activation energy. All right, so overall, this objective was very heavily related to getting that foundation for this entire unit. The rest of the objectives should be a little bit smooth sailing, but again, this was more of a foundational objective, gave us a lot of information, but it should prepare us for the rest of the objectives.